All right, welcome everybody. My name is Niklas Gustafsson. I'm a software architect in the parallel computing platform team, part of Visual Studio. I'm going to be talking about taking a look at what's inside the concurrency runtime and also talk a little bit about how to extend it. I'll spend about 10 minutes introducing this stuff, and we'll spend 15 minutes on going through the internals, and then we'll look at code, and we'll look at how to do the actual extensions using the APIs that are public. The key takeaways that I hope that you get from this presentation is our motivation. Why are we building this concurrency runtime? When is it going to be available? I can answer that right now, VS 2010. How do I build if I have this algorithm that I know or suspect can be parallelized using the runtime or parallelized in general? How do I build it on top of the infrastructure that we're providing so that you don't have to reinvent that wheel? And how do I build, if I really want to go in the deep and build my own work scheduler, taking advantage of the runtime's infrastructure for resource management, how do I do that? And that'll all make sense in a few moments. What you will not see is managed code. This is a C++ talk, so if you were hoping for something else, then I won't be offended if you leave. You will not see robots. This is not a talk about the CCR. We're not going to see we're going to see one demo, but it's not going to be much about flashy stuff. This is we're going to be writing code in this talk. And we're not going to see impressive performance numbers. This is not one of those talks. This is about how your impressive code and algorithms can be built with our infrastructure. And so you'll be providing the impressive numbers later. Well, I don't want to waste people's time, so it's better to be upfront about it, you know. Why are we building a concurrency runtime? We really see this as the same reason why there's a C runtime. There's some basic infrastructure that really you shouldn't have to do yourself. You shouldn't have to do your own console I/O. You shouldn't have to do your own memory allocation and heap implementations. And you shouldn't have to do all the thread management that is necessary to do a concurrency library. So we'll take care of that. And we'll ship that, in fact, in the C runtime. It'll just be there. You won't even have to know about special DLLs or redistribute special DLLs. It'll just be there. We want to unleash the power of parallel hardware. That, as we all know, it's no secret that parallel hardware is the future of the industry. And we want to do this through a rich ecosystem of languages, libraries, and tools. There's no single thing that will make this a feasible environment to program. And we also believe that there's no single company that has the magic bullet that will just make this all easy. We think that there's no single algorithm that's going to make all this easy. There's going to be a number of solutions, there's going to be a number of languages, there's going to be a number of algorithms and companies that will together provide the overall solution to unleashing this power. So what we're doing is we want to build a common, extensible infrastructure for partners and customers and just, even application developers that have a particular application-specific algorithm or library that you need or want to put on top of this infrastructure. As just an example, Intel has announced at IDF in August their support of the concurrency runtime with threading building blocks and their OpenMP implementation, as well as supporting it in the Intel Parallel Studio tools. I just want to set the premise here for why we think there's a new world and why we can't just live with threads. And if you've gone to the other parallel track or the other parallel presentations, there's been a lot of talk about task-based programming instead of thread-based programming. But basic issue is when you have abundance of resources instead of scarcity of resources, the solutions that were designed for managing the scarcity really don't apply as well as they used to. Efficiently maximizing throughput is a key issue here. How do you keep your cores spinning? How do you keep them busy? We don't care as much. We still care about fairness, but it's not the central issue because there's going to be plenty of resources to go around. We also think that scheduling needs to be less random in order for it to be efficient. Random scheduling of things happen, to be really bad for cache locality, for example. And in the end, how your memory is being used by your algorithm is going to determine a lot about how efficiently it runs. Particularly as the levels of caches and the hierarchies of memory become deeper and deeper, and we really don't see much of an end to that. In fact, it's more likely to just get worse and worse. In Visual Studio 2010, we're shipping a whole bunch of things. We've talked about these in both the native and managed tracks. And I'm going to focus on these two pieces in this talk. It's kind of the infrastructure for the native side of the story. And I have James Reinders from Intel here with me to talk a little bit about what they're doing with the concurrency runtime.
Thanks, Nicholas. So at IDF in August, we announced our Intel Parallel Studio project. And as part of that announcement, we announced that we're supporting the Concurrency Runtime project with Microsoft. That was incredibly important to us. So I wanted to say a few words why we would say that and why this talk is really important if you're considering building any tools or infrastructure that use concurrency. You want to take advantage of the concurrency runtime for the same reasons we decided that we need to back that and work with Microsoft on it as well. The key is we want to make sure that as more and more parallel solutions emerge, that they're compatible with each other. So we've had this challenge ourselves for a little while. We've had an OpenMP implementation, and we used to have our math kernel library used to do its parallelism on its own, but then we converted it to use OpenMP so that it didn't compete with each other. The next thing, though, along came our threading building blocks project, and brilliantly we create our own thread pools for that, separate from OpenMP. And it's not that big of a deal. When you have 2 or 4 processors, it's not such a big deal having twice as many threads created as you need. Microsoft's implemented their OpenMP. They create their own thread pool. So now it's theoretically possible that you could create an application that uses our math kernel library that uses OpenMP, do a little threading building blocks, use Microsoft's OpenMP, grab a Nehalem processor with 16 threads, put 2 of them in a system. You can get 128 threads created in a program like that when you really should be creating 32. You can quickly get an explosion. That's a big problem. And there's no good reason for it other than each team was implementing their own wonderful work-stealing scheduler. So Microsoft's undertaken a very large task here. There's a reason why we didn't combine our runtime from OpenMP and threading building blocks. It's not a trivial task. And so when Microsoft said that they wanted to put together a concurrent runtime, we want to be very supportive of that because there's enormous advantages if all of the tools that have a little friendly competition, agents, libraries, parallel patterns, threading building blocks, OpenMP, if they all use a common concurrency runtime, we can avoid an explosion of threads that's not in any of our best interests.
Okay. Thank you, James. All right. So we're going to get into the internals now, get a little bit more in-depth and a little bit more technical. The resource manager is the core piece underlying the rest. And that's where, regardless of, if you're going to do any integration with our runtime, you will be building on top of at least the resource manager. Its purpose is really very simple. It's to serve up processors. It's to manage who gets to run processors. Note that we're not saying threads here. We're saying processors. Processors is the thing that we schedule in the concurrency runtime. And again, this comes back to the resource abundance scenario, where it's not really about scheduling threads. It's about scheduling the things that the tasks will run on. In the current family of operating systems, we will be supporting this management of resources only within a single process. And this actually extends to Windows 7 as well. In the future, there may be developments that allow us to do a better job of that. But right now, it's going to be intra-process functionality only. All right. Okay, I already spoke to the last point here. Let me just show you by an example of what the resource manager will be doing here. And this goes to James' point about multiple schedulers, like TBB having a scheduler, PPL having a scheduler, and OpenMP perhaps having a scheduler. If they're integrated with a resource manager, we will have, for example, a scheduler A come in and say, I need between 1 and 8 processors. It's actually not very uncommon to say, put a ceiling on how much power you want. Because, for example, if you know that your algorithm tops out at 8 processors, you really don't want 10, even if they're available. You just want 8. And if you're running, particularly in scenarios where you're running on multi-core, multi-proc, so you have actual separate sockets and separate processors, there's a cost of spanning 2 processors that is not there if you are on the same processor, L3 cache, for example. So scheduler A comes in, and it tells the resource manager, I want 1 through 8 processors. And the resource manager allocates those yellow processors, or cores rather, I should say, to scheduler A. All right, life is good. Scheduler B comes in and asks for 1 to 12 processors. It said, of course, it needs 12 cores. Or it could use 12 cores, but it can live with 1. So the resource manager says, well, I have 8 available, so I'll give you 8. And that seems fair. We don't know anything about scheduler B or scheduler A except what they're declared that they need so far. So time goes on. And what the resource manager will be doing periodically while scheduler A and scheduler B are running is collect statistics from them on their internal queue lengths and other things, how quickly they're able to dispatch work and so on and so forth. So over time, the resource manager gets a little bit smarter about what's happening in scheduler A and scheduler B, so it starts reevaluating things. And at this particular point in time, we'll imagine that it has decided that scheduler A is making less efficient use of the resources than scheduler B. Or, for example, it has shorter queues, for example. Less work is building up in scheduler A than in scheduler B. So it seems only fair that to maximize throughput in the overall system, we would take some away from A and give them to B. Okay? So B now has 10 cores, and scheduler A only has 6 cores. And things continue. And we can have other reevaluations of this, but at some point, maybe scheduler A goes away and now relinquishes all its cores, at which point we knew from the beginning that scheduler B had declared up front that I could use 12. Well, there's no reason in not giving scheduler B those extra resources because it said it could use them. And so we do, because they're otherwise risk being idle. And again, it's about maximizing throughput, maximizing resource utilization. We're not going to give it more than 12. Even though we have statistics about scheduler B, it's said up front that it's not, it really doesn't want more than 12. So we're not going to give it more than 12. Okay. On top of the resource, so that's really what the resource manager does. It's a singleton. There's one resource manager in the entire process, and this is really what it does. It just doles out cores, both statically when you first ask for them, and then dynamically as it gathers statistics over time. And it's NUMA aware, and it understands as much as it can about the topology of the architecture and makes decisions heuristically based on the statistics that it gets and the actual physical allocation of cores to schedulers. On top of that, what we have done is we've also written a scheduler, and this is a replaceable scheduler, but this is a scheduler that sits under PPL, which Rick talked about in his talk on Monday, and also under the agents library that Rick mentioned in his talk on Monday. So both under the parallelism based on control flow type of, and tasks type of library, and the data flow library that agents represents. A scheduler is, in our terminology here, similar to a thread pool. You can think of it logically as a thread pool. Its sole responsibility is getting work items executed. It really doesn't do anything else. It's policy driven. In other words, you can set certain parameters that you set when you create the scheduler. They don't change during the lifetime of the scheduler. For example, you can say, as from our example previously, I need at least 2 threads or 2 cores. When I say threads, I mean, in this scenario, I mean hardware threads. I need at least 2 cores, but I could use as many as 8 or 12 or whatever the number is. Those are policy elements. And I can say other things. I want them run at this thread priority. The worker threads that get allocated to me, I want them at this thread priority, high, low, medium, whatever. I may want to allocate stacks with 250 megabytes instead of 250 kilobytes instead of 1 megabyte, and so on and so forth. Those types of data is bunched together in a single policy for the scheduler, and that's used when you create the scheduler. There's some basic scheduling primitives. There's an event class and things like that that we can leverage. And this is also an important aspect here, is that you can have multiple scheduler instances. So you can actually factor your application or your even library algorithm into multiple partitions that you want them to run away from it, to execute away from each other. So you want negative affinity, in other words, right? You want this part of your application to run on one set of cores. You want this part of your application to run on a different set of cores. And you want this because you know that there's something you know about your application that tells you that that's good for your cache management, for example. Or you have a NUMA architecture and you really don't want things to be moving between NUMA nodes. Okay, so a couple of scheduler concepts. We have a virtual processor, which is a proxy for the hardware thread, the hardware resource. It's a worker thread also. There's a one-to-one correspondence between virtual processors and worker threads. We have a context, which is a dispatcher. That's the scheduler's main logic for deciding which work item goes next and actually invoking it. So that's the context. We have something called a schedule group, which is a collection of queues internally to the schedule. And we have work items. Well, there are 2 kinds of work items. Those that are scheduled through work stealing. And we have lightweight tasks that are scheduled via FIFO queues. I'd like a show of hands. Who are familiar with work stealing? Okay. There's enough that I have a couple of slides explaining work stealing here. So I'll just go through those with enough people who didn't show their hands here. A traditional thread pool typically works, at least logically, like you have one single global queue for the process where work items are entered in some order. And they're taken out by these worker threads that are typically allocated dynamically, and they're injected as you see load go up and down on the system, and some stall on kernel I/O and things like that. But the items come out of that pool, and new ones are created, and they go back to the same pool. And there's nothing that says that the items that are created go back to the same worker thread that they came from. In other words, if their data happens to still be in cache, we're not taking advantage of that because we moved it to another worker thread, which is probably running on a different core. Work stealing works a little bit differently. There's still a global queue, and into which we put tasks, and they're still being picked up by worker threads, but the worker threads also have local queues into which they put any work that is spawned from the work they picked up from the global queue. All right? So task 2 here spawned out 3, 4, and 5 onto the local queue, and then when task 2 is done, the worker thread 1 has to pick up more work. Well, it picks it up first from the local queue, its own local queue. And what's a little bit odd here is that we're actually executing the last created work item first. So it's more of a LIFO order than a FIFO order, but that's actually good for caches because the work item, at least statistically or probabilistically speaking, because the last work item created is more likely to have an overlapping working set with the parent task. But it's all probabilistic, of course. There's no proof of that. Well, worker thread P also runs out of work. It discovers that both its local queue and which it would prefer to pick up from, and the global queue, which is still there and might still have work items, are empty. So now it takes one from somebody else's local queue and it steals it. And this is why the algorithm is called work stealing. And then it will spawn more work on its own. Okay? So the scheduler data structures that we use inside our scheduler we talked about the virtual processors, and those are allocated by the resource manager for us. This is how the resource manager tells us that we got a number of processors. And we allocate context to those. And at any given point in time, there's exactly one context per virtual processor. But when the work that happens, and the context again is the work dispatcher, so the actual task work will be invoked from the context. So this is stack associated with that context. When a context is then blocked, for example, in the kernel, we have a pool of free contexts that we have used before, perhaps, and we disassociate the blocked context with its virtual processor and pick one of the free contexts and associate it with the virtual processor and continue and start new work on it. We restart the dispatching loop on that. All right. The contexts then each have a reference to the circular buffer of schedule groups. And schedule groups are logical groups of queues. And we have organized queues together because we think that the work that's put into them have something in common. And this is something that the application typically will do, or a library more commonly will do. It will, for example, in the agents library, we will put all the work associated with a particular agent in one group. Right? We'll see when we start writing code here also how we put work that goes together in a schedule group. So the context will go and look at a schedule group, and it'll be at a particular point in the circular buffer at any given point in time. And it'll continue to get work out of that schedule group until there's none to be taken. And then it'll move on to the next schedule group and look for work there. So there could, and it could be a many-to-one relationship here too. There could be more than one context looking at the same schedule group at a point in time. So there's potential contention there, and we were able to handle that. All right. So let's take a look inside the schedule groups and see what collections of queues there are. All right. We still have the unblocked constants. They're actually not inside the schedule group per se. We have yes, they are. Sorry, I'm confusing myself. These are not the free contexts. These are the unblocked ones. Okay, so the unblocked contexts are contexts that have come back from their kernel block. They're ready to run again. All right? But we don't want to overload the processors. We don't want to oversubscribe them. So we try to keep them off from working. And Windows 7 makes that easier than Windows Vista, for example. So there's improvements in Windows 7 that will help us with this. FIFO, we have a list of these FIFO tasks that I talked about. And there's actually, there's one logical single queue of these tasks, right? But they're actually also divided in schedule groups. So the physical queue is actually divided into these groups. And then we have per context work stealing queues, all within each schedule group. Now, they're obviously allocated as a sparse, so this forms a matrix of schedule groups on one axis and context on another axis, and there's, in the cells there are these work stealing queues, and obviously it's a sparse matrix because we don't want to allocate all that memory. The dispatch pseudocode, and as I was just looking at this 5 minutes before the presentation, as everybody was filing into the room, I realized that this is actually not a very good representation of what actually goes on. What I wanted to demonstrate here is that we actually have the dispatch logic works like this. We have an outer loop that really goes on until we're told to stop. And one reason for, really the only reason for being told to stop dispatching is that a processor was taken away from me by the resource manager, right? Then within that loop, we then go through all our groups. This is the circular buffer that we go through. And within that, we look for more work in a particular order. And this is the thing that is better expressed as just going through the unblocked work, get new work, and stealing every time through the loop. But what we're doing is we're looking first for unblocked work. We really want to finish work that started, because if we pick up new work instead of finishing work that we had, we're actually using a lot more memory. So it's better to finish what has been started. So unblocked work is things that came back from kernel blocking situations, for example. If we don't find unblocked work, then we get new work. And we get it from that FIFO queue of lightweight task. That's new work. And then the last thing we do is we steal. Now you notice here that if you saw in the diagram, there's a pop off of the work stealing queue that isn't mentioned here. And that actually happens outside of the dispatch queue. That happens locally in the logic that pushed it. So it actually happens in the code that you write in your algorithm. And I'll point that out when we get to the code. So this is at the top level loop, and the pop actually happens. The work stealing pop actually happens at the leaf activation frame of the stack. Okay, that's a brief discussion of the internals, and I thought that we should talk a little bit now about the APIs and how to extend this. And we'll first talk about the API between the libraries and the scheduler. And I'll go through some of the important APIs. The scheduler, we've talked about this previously also, of course. This is really an overall collection of dispatchers, is one way of looking at it, with a particular common set of policies. We have a scheduler policy, which contains a set of policy elements. We have a schedule group, which confusingly is called task group in the CTP. And this supports task scheduling FIFO queues, and it also contains the work stealing queues, but it doesn't have the APIs for the work stealing queues. Contexts, which is well, we talked about what that is. And now, task group, little lowercase task group and structured task group, and we have an event. Now, if you're confused about the naming conventions here, we're actually following the rule that we're using COM-style names for the scheduler and the resource manager, and we're using C++ standard template library conventions for the things that surface in PPL on agents, and task groups and structured task groups actually surface all the way out, and therefore we're keeping the C++ naming conventions. So there's actually some thought behind the madness here. Is that pretty clear? Okay. All right, so the first thing I'm going to do is I'm going to do a very common algorithm, and this is actually something that's going to be shipping. I'm going to do a really naive version that hopefully demonstrates how to do it for real. We're going to be shipping a reduce actually in the PPL library when the product comes out, but there's not one in the CTP. So I thought I should build one. Okay. So reduce. Oh, I had a slide on that. Never mind. So what reduce does is it takes a vector of values of some type, let's say integers, and produces a single value from it. So summing, averaging, min-max. There's a lot of problems that are expressed as reduce problems. And if you have a function that a reduction function that is a little bit more complex than integer add, then the actual element by element reduction can take a lot of time. It can itself be parallelizable, but just the combination of them can take a lot of time. If you have really, really long arrays, it can take a lot of time. If you have millions of elements in them, or billions perhaps. So there are opportunities for parallelism here, both from the length of the vector and the cost of the operation. And I'll show neither of those. I'll just show the code. Okay. We're going to do integer add over a vector. And we're going to push some. So I haven't written the code here yet. It's there. But this is this is what we're extending the library with. And this follows the current standard template library accumulate function that's serial. And we're trying to, in all our PPL APIs, we're trying to follow the standard template library as closely as possible with names. So we're calling it accumulate, rather than reduce, because that's what the standard template library calls it. And again, I'm going to have a naive implementation of it. But even though it's naive for reduce, we're going to do it through a recursive subdivision of the vector. And recursive subdivision is a very common pattern when you try to parallelize things like this. Quick sort, merge sort, for example, are good candidates for that. So we have a vector, and we're going to push some values into that vector. We're going to get the number from the command line, and we're going to accumulate them. And we're implementing this on top of iterators. And so the accumulate function itself takes an iterator first, which is where we're starting, iterator last, which is where we end, an initial value, and this is important for reduce, that you have to have an initial value that is sort of your starting point. For addition, it's 0, and for multiply, for example, it's 1. And then we take the function. Okay? And these are all template arguments to the function. Our invocation of that, we're going to do it for 64-bit ints. The invocation of that looks like this. We have the vector. It's the begin iterator, the end iterator, the value 0, and the standard plus function object there. Okay. So I'm going to just write this. The first thing we want to do is we want to check for 0 items. In which case we return the init val. Okay. If num items is 1, so now we have one item, and we need to combine that with the init val. Okay. And notice that the worker doesn't actually take 2 iterators. It takes a single iterator and the distance between them. And we also need a special case 2. And we'll very soon get to the interesting parts here. Okay. So far, there's absolutely no parallelism in here, of course. Now, we're going to do this subdivision, so we already have the distance between the 2 iterators. We know it's greater than 2, so it's starting to get interesting. So what we do now is we're going to find a half point, and we're going to give half the array to plus minus 1, of course, right? Half the array to one task, and we're going to do the other half ourselves in this thread. There's no reason to create more than one new task, right? Because we already have a thread to execute part of it on. So we'll find the half point. And we'll create an iterator that represents that half point. OK, so we have that part done, and we have to capture the first half, the first part of the result in something. And we will now create a task group. So we're going to, the reason we're creating a task group here is that in this API, you have to have a task group to run a task in. We debated many times whether we should have a way to just run a task on its own, but that's not how it's implemented. Then you create a task handle, and here's we're relying on C++ TR1 function objects, and we're relying on lambdas. Lambdas are the greatest thing ever, and will make your life much easier. They're in C++ OX, it's a draft standard, but we will be supporting C++ lambdas in Visual Studio 2010. So what it allows you to do is, just like in C#, for example, you can just write the function that you need in line and capture it in a variable like that. And here I do my result 1 equals my naive. So this is my actual recursion. And my init val stays the same. OK, so that's my result. Now, just creating a task handle doesn't get me anything, so I actually have to start it with tg.run, and I have to wait for it. One of the things, actually, you notice that I use task group here. I can use task group, but task group is less efficient than a structured task group. So I'm going to use a structured task group. One of the things that is different there is that if I'm using a structured task group, I'm promising the system that I will have finished all the work that I created under that task group before I return from this function. In other words, before the task group is destroyed. So it can use more efficient allocation of memory. It can allocate things on the stack instead, which is a good thing. All right, so we have a little bit of work left. We need to create something to capture. I'm just going to copy that. And here we want to start at the midpoint. We want to do num items minus half instead. And then we're pretty much done, except we need to also combine the two half results that we got, result 1, result 2. Compile it. All right, so let's see if it works. Reduce something like 15, should be 120. OK, it worked. So the idea here, what I'm showing here is how to use work stealing in a new algorithm. The work stealing happens at the point of the wait. So to walk through here, we created a structured task group that will hold some work stealing queues. We create the task. We describe the task right here. We run it here. So we start it here. All right? That actually pushes it. All right? Onto the work stealing queue. And then we do this work while that thing is on the work stealing queue. Right? And if we're lucky, if there's an idle processor, it gets stolen. If we don't have an idle processor, during the wait, right down here, it'll get popped and run right in line during the execution of the wait. And that actually happens to be, all things being equal, a more efficient way of running it, because we started its work and it's sharing this vector, which is probably, at least parts of it is in cache. And so it's going to be a very efficient way of doing it. But if we have an idle processor, we're OK with somebody else running the code. All right, so that's the reduction. I'll switch back to this and take a look at our next example. an alternator. This speaks to the agents library. How many saw Rick's presentation here yesterday? Okay. So I'll do the demo that Rick did yesterday to show what I mean about what this is all for. So if you have seen this before, it'll be old news. So what we have here is we have an image application. It's given a directory on the drive and asked to go look for all the images under that directory at any level. And so there's a part that goes and searches for files, and then it loads the image up. That's the next step. And then it does a blur filter on it and a glow transform on it, and then it displays the picture. Okay? So we can do that serially, or we can do that in parallel. And how we do it in parallel is we build a pipeline of stages. And the pipeline is actually much faster than the serial performance, because we have a agent that spits out the file names, and we have one transform stage in the pipeline that reads the file from disk, and one that does the transform and then sends it over to I'm not going to show the serial version because it takes too long. I'm just going to show the parallel version right here. "11 images in about 5 seconds. All right, that doesn't say much, but we have a mode here where we add this load balancer thing we call an alternator in front. And what that means is we're actually having several pipelines, and we're sending work to all of them so that they can, not only do you get parallelism from the depth of the pipe or the length of the pipeline, you're also getting parallelism from the pipelines running in parallel with each other. So there's sort of a matrix of parallelism there. And in fact, the transforms themselves, the filters, are parallel. So you're actually getting a third dimension to that by running that in parallel with the parallel 4. So we got a little bit of a speed up, all right? It's not hugely impressive, but we did get almost a 20% speed up there. All right, so what I'm going to do is I'm going to build that alternator because it does not exist. And it's not going to be in the product either. But it's really easy to build. So do try this at home. Okay, so we have a really simple application, and we're using lambdas here again. This time we have a function. We have a lambda here that prints out something. It prints out an integer to the console with a prefix. And we're going to run it in 2 stages. So we're going to run up to 15, and we're going to run to 30. And we want to capture that with an event. This event here, by the way, is a runtime aware user mode manual reset event. So it's a little bit lighter weight than other things. Okay, so what we're doing here is we're actually creating we're using even more lambdas here, and we're creating 3 versions of this function, one that says A, B, and C. And we're going to so those are calls, and if you remember Rick's talk about agents, calls are endpoints in a data flow. That's where the data eventually winds up, and all you see is side effects rather than transformations. So we have 3 calls, one for A, and one for B, and one for C. And what you kind of would expect is that if you put a buffer in front of it and you link up more than one of these to a buffer, that they would be getting half each. And you sort of kind of expect that. But our buffers don't behave that way. They are priority-based buffers. In other words, the order in which you're linked in gives you priority for the messages that are coming through through the buffer. So if we build this thing as it looks now I put this unbounded buffer in front here, and I'm linking up the 2 calls here first. I'm going to run with 2 targets first, up to 15, and then I'm going to link in a 3rd target, and I'm going to run to 30. If I build this and run it, No. I see that A gets everything. So that's not quite what I expected if I just thought about a buffer like that. But again, it's priority based. The first thing gets everything. Unless it says, I don't want it, in which case the other ones get a try. Okay, so we're going to fix that. We're going to build a buffer that behaves differently. So we're going to call it an alternator, and we're going to derive from it. It's going to do true round robin. And when we're doing a round robin, the first thing we need is we need a point. We need to keep track of who got the data last. And we'll keep track of that in an integer, and we'll call it next. And we'll initialize it here. All right, so as you can see, alternator derives from unbounded buffer, right? And we make it a template class. Now, because all our agent blocks are template classes, we can go look at the source. And we'll do that now. You can see here that we actually just created one constructor. In a real world case, we would want to have about 6 or 7 constructors because these blocks typically take a filter which decides whether to accept the message or not. You parameterize it with giving it a particular scheduler that you want to schedule the work on, or even a task group. Again, these are called schedule groups in the final product. But for simplicity, we're just going to do that single parameter, the default constructor. All right, so we can just build this, and we'll build this, and we'll see that, of course, it behaves exactly like the other one, because we didn't actually change anything. All right, so we're going to go take a look at the code, and there's a when we ship the product, we'll have examples and descriptions of how to extend this in documentation. But for right now, I'll just say that this propagate to any targets is a core logic. It's the core logic behind propagation of data from one block to the next. And so I'm just going to go lift that and use that in our code. I'm not saying that's the right thing to do, but it's convenient. So what we do here is we take a lock. So what comes in as a message, it hasn't been put into our data structure yet. It could be null, so we have to be careful about it. If it's not null, we put it in a queue, and then we take the head of the queue out. If they happen to be the same, which means we actually put the thing we put in is at the head of the queue. This is an in-order buffer, so we guarantee in-order delivery. Order preservation is very important. And if things work out, in other words, this is at the head and so on and so forth, then we need to distribute it. We need to send it somewhere. Okay? We do that by going through, we go through all the messages. In the while loop, we go through all the messages in the queue. We start with head, and we then go through all the targets and offer them one at a time to the targets. So we always start with the first target, and if it accepts it, we're done. We go on to the next message in the queue. There's also this possibility that is reserved. I'm not going to go into. There's a two-phase protocol that actually some of the blocks will be involved with that this covers. We'll just care about the accepted case. That's all that's going to happen now anyway. So we'll actually take advantage of our .next or our next thing here. We will normalize it to the actual number of targets, like that. Targets can come and go. So from the last time we were here, it might have been lowered. So we'll just take it modulo t count. And t count was the number of targets in here. And in here, the loop where we're going through the various targets, we're going to create a new local variable, add it to our count, our I, and do modulo t count. And then we'll use j here. Now, this still will only next. We haven't updated next yet, and we'll have to do that here. so that we actually, next time around, we give it to somebody else. And we'll build, and we'll see if it works. Yes. So here, in the beginning up to 15, we see A getting the evens and B getting the odds. After 15, we see C coming in and getting every third, and B getting every third, and A getting every third. So that's our true round-robin alternator, which is what we wanted, and which is how come this speeds up. Okay. So I'll go back to my slides. Yep, sorry. So the resource manager interface is mostly relevant if you ever care about writing your own scheduler. This may be because you have a scheduler that already does a good job, but you want it to fit into the resource manager and cooperate, like James was talking about earlier, cooperate with the other possible technologies that are built and resident in your process. Or it can be that you have tried running your algorithm on top of our scheduler and found that some particular intuition or knowledge about your algorithm isn't well supported by our scheduler. I can't think of a situation like that, but it's certainly conceivable, and we certainly don't want to handicap you if that's the case. In that situation, the resource manager is also something to consider targeting. And we're going to build a scheduler in a second. Or we're not going to build it. We're going to look at a really, really simple scheduler and single-step the APIs so that you can get an understanding for the level of complexity. And it's not too bad, actually. The resource manager APIs that are important are iResource Manager. And again, we're using COM-style naming conventions here. It's all capitalization here. iResource Manager is an interface for the RM singleton. Again, it's a singleton per process. And you use this to make requests and register your schedules with the RM manager. We have iScheduler, which represents a scheduler. And the RM is going to use that interface to call back, to give you threads, to demand that you give them back, and so on and so forth. All right? iVirtual Processor Root is a processor representation. iThread Proxy is representing a worker thread. And all worker threads are allocated by the resource manager. And, iExecution context, which is the RM-facing interface of the context that we saw used earlier also. The initial exchange between the scheduler, and we'll go through this in the code also, it looks like this. We create a resource manager and get a pointer back. We request some initial threads from it. And the resource manager will then say, well, in order to give you that, I need to get your policies so that I can create the right number know how many threads you want, what kind of stack sizes they use, what kind of priorities they need, and so on and so forth. So it asks for the policy values. It comes back later on and actually returns from request initial threads. And at a later point, there's a line missing here. It calls add threads on the scheduler, actually giving you the virtual processors. You then call activate back to say, now's a good time to give me a worker thread. So even though you've been allocated processors as a scheduler, you don't have to take them. You don't have to use them right away because you may not need them for a while. You may need them eventually. So when you're ready to use them, you call activate, and at some point after activate, the resource manager is going to call back on the proxy that it created, or the worker thread that it created, is going to call your dispatch logic back, and we're off to the races. So I'm going to just go through a simple scheduler. It's not going to be a work-stealing scheduler, but it's going to show you all these interfaces. And we're going to have things like that also when as sample code and documentation when this goes out, so that we make sure that it's very easy for you to write this kind of code. Now, our actual application here is ridiculous. It's a parallel implementation of Fibonacci, recursive. It's absolutely the wrong thing to do, except when you want to create lots and lots and lots and lots of tasks, which Fibonacci will do for you. But anyway, what we're going to do here is we have this global scheduler, and we're asking for 8 processors. Okay? I actually only have 2 on this laptop that I'm running this on, but I'm going to ask for it because, well, I think I can use as many as 8 cores, I mean, not processors. And we're going to do, to actually add a little bit of work to the Fibonacci, we're going to do a spin, and then we're going to, well, here's the parallel version. We're going to use lambdas to start one task here, and use another lambda to start another task here, and then we're going to wait for idle. This is in our scheduler here, this is kind of corresponding to the task group .wait that we had in the concurrency runtime scheduler. And we're going to time what a serial version and a parallel version, how they do. Okay, let's single step here. We're going to debug this. So the first thing that happens is that the static scheduler that we created gets constructed, and we call init here from the scheduler constructor. Let me do this also so we see better. And we're going to make a call to create resource manager. This gets us back the singleton. If it didn't exist, it's now been created, and we can use it down here to request some initial threads. What's going to happen if we step over that is that we're going to be stopped here. So we're actually being called back in the same logical chain here to get the policy, just like that sequence diagram showed earlier. If we step through this, we can't see the code anymore. But if we continue, we're going to wind up here in add threads. So this is where the RM has decided how many we're getting. All right? We asked for 8. That's the max threads policy we sent in. But our count is 2 because the resource manager, we didn't say how many we needed. If we had said min 3, then we wouldn't have come back here at all because there are only 2 processors on this machine, 2 cores on this machine. We would have gotten an error because we asked for. Would either have gotten an error, or would have gotten oversubscription, which is where the resource manager decides to actually create more work, give you more virtual processor routes than there are hardware cores. So oversubscription is something that I'm not going to go into in detail here, but there is, if you really do want more threads than there are cores, you can ask for that. But the default is that you get one worker thread per core. Okay, so we just go through this. And this is where we now call activate. So we have our virtual processor routes, and we decided, yeah, we want everything you gave us. So we're going to call activate here, and we only have 2. So eventually we wind up in dispatch. And this is now where the scheduler goes through and has some logic that you came up with to actually schedule these work items that you came up with some mechanism of storing in some data structure. In here is just a very simple list, but we can now continue and run this. I can also run it outside here, and we'll see. No, it's not that one. And so what our ridiculous Fibonacci implementation does serially is it speeds up 50%. All right. If we had used work stealing, it would have been much more than 50%. But this was a FIFO implementation, and we actually have a very simple scheduler, and we get a little bit of speed up. And you writing your own scheduler can just imagine how much better that will be when you actually spend more than 5 minutes doing it. Okay, so back to the end of my presentation. Concurrency is a broad problem. It requires broad solutions. We don't think that there's a single model or a single algorithm or a single runtime that's going to address all of those problems. We fully expect that you, either as a third-party ISV or partner of Microsoft's or even application developer, there are going to be things that you want to do that's not in the box. There's lots in the box. But there are going to be things that you need to do that are additional. It might even be as sophisticated as writing your own scheduler because you just know better how to schedule certain things. We are building a foundation for you to leverage because your code in that case is going to be used together with other libraries, other algorithms, and other implementations. And we want it to work well. And so by leveraging either the resource manager or the task scheduler that's built in, which are available in public APIs, they're going to be well documented, they're going to be coming with examples, and we're going to make it all easy for you to do. We think that we're providing a robust and efficient foundation, and that we're making it easy for you to hook in at many levels. All right. There are other parallel sessions. Most of them actually happened already. But there's a symposium tomorrow where we talk about various topics related to the future of parallel computing also. We'll talk about the hard problems, application architectures, and we'll have a panel discussion with a few members. So this is the primary site to go and find out more about what we're doing for parallelism and concurrency. And I'll just open for questions.